So continuing with our problem, we want to get the probability that we get a sample mean as far away from our null hypothesis of the population of Santa Clara students having an average age of 19.75. So we want to detect the probability that we want to calculate the probability that we get a sample mean as far away from 19.75 as 20.15 is away from 19.75. And it can be far away on either side, so it can be far away on the right tail or far away on the left tail. And again, since the normal distribution is symmetric, the probability that you're far away on the right tail is the same as the probability that you're far away on the left tail. So we just need to calculate this one, this probability here, and multiply it by 2. And that gives us the probability that you're as far away from 19.75 as 20.15 is away from 19.75. So that probability is then the probability that the random variable x is less than 19.75. If we take 19.35, I'm sorry. If we take 19.35 and subtract 19.75, the mean of the distribution, and divide by the standard error of this distribution, then this probability is for the standard normal distribution with mean 0 and standard deviation 1. And we can calculate that very easily by looking it up in R. So that's the probability. If we take 19.75, 35 minus 19.75, we get minus negative 0.4, and then we divide by the standard error, which is 1 over the square root of 200. So that's negative 0.4 times the square root of 200. So that's going to be then the probability of being less than negative 5.65 in the standard normal distribution. We multiply that by 2. So we have 2 times, because remember we have this tail and this tail. So again, this statistic, which we'll often call a t-statistic, this t-statistic, or a t-stat for short, this t-statistic follows a standard normal distribution. So we can look in R, where we have the command in R, p-norm, minus 5.65, and we get 8.022 e to the negative 9, so that's 9 zeros, scientific notation, right? 9 zeros and then 8022. So this is a very small number, and remember we have to multiply by 2 to find the probability, so 2 times that norm is then 1.6 times e to the e to the negative 8, so that's 0.8 zeros, 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 6. So this is a tiny number. So these tails here are tiny, right? So the probability of our true mean is 9.75. The probability that we get a sample of 200 people having a mean of 20.35, right, is 20.15, I'm sorry, is extremely unlikely. The probability that we'd find a sample as far away from 19.75 as 20.15, as far away on either side, so we're doing this two-sided test, the probability that we'd find a sample as far away from 19.75 as the sample that we do find, which is 20.15, that probability is tiny. And so since it's so small, probably what we should do is reject our null hypothesis or modify our null hypothesis, or think that, well, maybe the mean age of students at Santa Clara is actually higher than 19.75. Maybe it's closer to 20. And if we right? With each sample, we could take more samples, of course, and every sample would give us more information. If we had more individuals, so we could do the survey of the whole population and get the exact mean. But this is how we'd go about doing the hypothesis test and thinking, since we have a very simple hypothesis test here. We think that the sample mean is 19. We think that the population is 19.75. Our sample of 200 students found a mean of 20.15. We determined using statistics that finding that sample mean would be very unlikely if the true mean is 19.75, so we should reject our hypothesis that the true mean is 19.75, and we don't have an alternative hypothesis to accept, so but our intuition would be, well, probably our mean is population mean is a little higher than that.